Hello and welcome. In this video, we're going to talk about how to make the flywheel as part of our assembly for our little steam engine here. So I have the print open and I'm going to start by looking at what features we need to have machined in this. And it looks like we have 7 quarter 20 UNC holes that are going to be going through, that they are going to be tapped. They have a true position of 5 thousandths with regards to datum A and datum B. The through hole, the tap drill size is going to be 201. When you look at the drill chart, that is the acceptable drill size for the quarter 20 UNC tap. I find that the holes are on 60 degrees increments and they are on a 1-inch 375 bolt hole circle. Taking a look at our datums, the back edge of the part is datum A, and then we have datum B is actually the diameter of the counter bore, and the counter bore is a 376 diameter plus or minus 1, so that's a pretty tight tolerance there. And just by looking at the print, I'm kind of surmising that this would be a lathe job. A couple of things here I'm looking at. I see that I don't have a diameter, a major diameter for this part right here. I don't know what the thickness of the part is. So we'll have to analyze those entities when we get to Mastercam. So let's switch over to Mastercam and see what we have here. Well, my goodness, it looks like I misspoke. This part is actually going to be manufactured on a mill. So we are going to manufacture a round part from square stock. So the first thing I want to do is I want to analyze the stock itself and see what size stock am I actually going to be using. So I'm going to go with the analyze distance command here, and I am going to go and get this top edge right here, and then I'm going to come over and get this bottom edge right there. And looking at the deltas here, I see that the x coordinate is 2 inches, the y coordinate is 2 inches, and the stock itself is a 1/2 inch thick. Okay, so now that we've determined what size the stock is, let's get a top view of this part. And in the top view, it looks like our X0 and our Y0 are in the lower left corner of the stock. I'll switch now to a front view and take a look and see where is the Z coordinate. And the Z coordinate is right in line with the part itself. So this is our standard SOP. What we are doing is we're taking the top of the stock minus 20 thousandths is where Z0 is going to be. So that establishes where our work coordinate system is for this part. And what I want to do here, before I get into all of the other parts of Mastercam that we're going to be looking at here, is I'm going to go and shut off the stock. So when we complete Op 10, this is what our finished part is going to look like. So we're going to be manufacturing this part on our Kurt vise. Our Kurt vise has the ability to open to a depth of 6 inches, so we can put in stock up to 6 inches wide. The jaws are actually 6 inches, so the depth is 6 inches. The width is 6 inches as well, so we can accommodate stock up to that size. And it works very well for when you have square or rectangular pieces that you're trying to machine. Now, when we get to Op 20, we turn around and we have a round surface here. Well, that doesn't work very well for our Kurt vise. So part of this lesson here that we're going to do is we are actually going to have a separate video on how to mill soft jaws. So we are actually going to this will be a Haas tip of the day video, and it will walk us through how to go and manufacture the soft jaws to accept this part in Op 20. So that will also be posted on Blackboard for you. So these are the jaws that we're going to use for Op 20. These have to be manufactured in our lab, and we actually cut this radius into the part on both jaws to accommodate our part, so that will actually be they will close, and the radius matches actually the diameter of the part that we actually are making in the lab itself. So now let's switch back over to our toolpaths. But before I do that, I'm going to take some measurements on this part so I can see what the physical size of the part actually is here. So I'm going to go up and analyze the entity here, and I'm going to grab this outer diameter, and it comes back that that outer diameter is 1 inch 850 thousandths. Okay, now I'd like to know what is the thickness of the part. So I will get out of this here, and let me go to analyze distance here, and I am going to pick the very top diameter here and then the bottom of the hole here, and I find that the delta for that is 1/4 of an inch. So the thickness of the part is 1/4 of an inch, and so now we have that information to move on and have that for ourselves here. Looking at our toolpaths here, we are going to start again with our facing operation. Here I will open this up here, and the tool that we're going to be using is our 2.5 inch shell mill. Our cut parameters are set so that we're going to go, it says 1 pass here. Well, that makes sense that the part itself is 2 inches across and the shell mill is 2.5 inches. So that should work out fine for us. Our linking parameters, and we note that our depth is 0, but the Z0 is actually 20 thousandths below the top surface of the stock. Thus, we'll be removing 20 thousandths from the part itself. So just do a quick back plot on this here. I notice it's coming from the rear to the front, and that should be right on the top surface of the part, which it is. So that was set up in the correct orientation, and so we are all set with the facing operation. So next, what we're going to do is let me turn our stock back on here, and what we need to do is come in and go and take a look at our second operation, and we are now going to do a roughing operation. We are using the dynamic mill sequence to make that happen. The tool itself that we are using is we are using a 1/2 inch rougher to complete this. Our comment is rough low OD, so we're going to be picking that would be picked at the bottom of the OD here. For our cut parameters, all right, so we are going to be using the cut method. We're going to climb. Our step over is 25%. Okay, the minimum tool radius is 30%. And the next thing that I want to look at, well, micro lift here is 10 thousandths. And our stock to leave on walls is going to be 10 thousandths. We have no stock left on the floor. Taking a look at our linking parameters, we are actually going down to a depth of 250 thousandths. All of these are absolute values, but I'm going to go back to the breakthrough, and the breakthrough is 10 thousandths. So our linking parameters is 250. The part thickness is 250, and we're adding with the breakthrough an additional 10 thousandths to get the radius of the tool down below the bottom of the part. So now to backplot this here, let me come in and select our backplot. What I'm going to do is shut our stock back off, so give us a little bit more clarity. And we're going to get this from, from the top view. And I probably should have left that stock on for this. And we're coming around. And it's kind of interesting how Mastercam does this. I mean, it comes around this loop and then it backs up and then comes back around. But that's just how it's programmed. And what I'm going to do is just pause this for a minute because I want to get a front view. And what I'm looking for when I get to the front view is actually this right here. Okay, I see that the tool itself is 10 thousandths below the surface of the material. And that's what I'm looking for. I'm just confirming that we have the depth is correct as far as for making sure that that is where it needs to be. I can go back to the top view here and let me go and turn on our, we see that we have a gap between the finished part and the orange that the tool made. So that is our 10 thousandths material left for the next tool, because this is a roughing pass that we're using to come around the part here. So this operation looks good. Let me go back to my tool path here, and our next tool path that we're coming in is with a contour. All right, so we are using a contour. Most of the material has been removed. We're down to depth. We just have minimal material on the wall. So let's take a look in the tool. The tool that of choice here is our 5/8 finish end mill. And the reason we're using the 5/8 finish end mill is because that is the largest tool diameter. We have our largest finish tool, and there are no inside corners or pockets that we have to deal with, inside radiuses. So we want to use the largest tool we can to minimize deflection. Our comment here is finish low OD, so we're pretty good here. Our compensation type, the compensation type for the tool that we happen to be using here is going to be wear. The compensation direction is to the left here. And coming down to looking at the stock on walls, well, we want to complete that. So that's why we wanted, this is a finish pass, so we want to bring that to the finish size. The stock at leave on floors is also at 0. All right, so there are no depth cuts because this part has all been roughed out. There's no need to put a depth cut. Our lead in, checking on our lead in, I see that our entry motion, we are tangent to the part. The length is 40%. Okay, the radius is also 40%. And those values were transferred over to the exit direction as well. Breakthrough, again, taking a look at the breakthrough. Now we do have breakthrough. The amount that we have is 5 thousandths. So now taking a look at our linking parameters, I see that the depth is 250 thousandths. But when we add in that breakthrough, that tool is actually going to be going at minus 255 thousandths from Z0. Okay, so now let's go and backplot this particular pattern here. Let me shut off my trace here. So you can see our lead in and lead out, and we just we're coming in, coming around. Well, it didn't show that. Actually, it does feed around the part here. Let me back this up here, and I'll just play this here. I said I will play this. There we go. Let me pause this for a second. What I'm looking at is zooming in and seeing that the tool actually is contacting the work surface, so there was no stock to leave. I'm now going to switch to a front view, and in that front view I'm expecting to see that tool diameter, the very bottom of the tool, excuse me, to be below the surface of the part, which it is. Now I'll switch back to my isometric view here and let this continue. And it continues around the part. Let me speed this up a little bit here. And our lead out, we have just a slight arc to come off of the part, and it's done. So that completes the finish diameter of the part. It brings us down to depth. So now, we're out of time, and I'll see you in the next video.